Okay, and I believe we are live now. All right. Um, let's go with screen one there, and we will open up our session zero cursor here for session zero of the game of programming. Okay, getting off to a bit of a slow start here. Make sure we Apparently, I cannot record until I upgrade Restream, but I'm not sure if I'm ready to do that yet. So, okay, we will go back to just me, maybe. There we go. All right. Quick test of, well, now I have this interesting case where I have a live stream on my YouTube channel scheduled at the same time that I'm live on Restream, and I don't know if that's going to break stuff. So let's go ahead and just delete forever. Okay. Unable to delete videos. Cool. Yeah. And dealing with a bunch of fucking shit with trying to go live here. Am I showing up live? Oh, I am. Hey, there I am on Twitter. 0 views. Cool. Um, Perfect. All right. Well, let me get my shit together a little bit here and try that worked, but all right. Sorry in advance for any coughing as well. I have been dealing with this damn chest cold for about 2 weeks now, and it's been really fucking annoying. Apparently, it's not COVID or the flu, and it's not bronchitis or pneumonia. It's not contagious. It's not anything except it's there and persistent. So I don't know what will. Don't know if that'll cause any issues. I tried to take some meds here before we started, so hopefully those will hold. All right. So, welcome to the game of programming. What am I doing here? Well, so a little bit of background. I've been a programmer now for about 15 years. Um, and I went through the traditional educational route, got a computer science degree, went into industry, got a master's in software engineering while I was uh, working in a library services nonprofit. And basically, I learned a ton of really cool engineering stuff in my time as a software engineer. Um, and then I moved into a little bit of e-commerce and then finally healthcare data. And that's when the pandemic hit, and basically I realized, like, I need to do more with my life than just programming. I wasn't feeling fulfilled. And here we are 5 years later, with a little bit more clarity on where I'm going in life, while there's a lot less clarity in where software engineering is going. And there's been this huge uptick in vibe coding, and I absolutely love giving people the ability to create things. But I've realized that a lot of people who don't come from a programming background run into a lot of really avoidable issues. And so, what I wanted to do is I wanted to put together a course on how to program without worrying about like syntax, right? Syntax is really important when you're learning a language and you're writing it by hand. It is not important at all when the AI knows all of the syntax way faster than you. And it can do it at a much more accurate rate than can even me. Like, and I've been doing this for a long time. So I don't think about syntax anymore. I think at a much higher level of abstraction. And so I wanted to approach programming through the eyes of games. Games are incredibly important for humans in so many ways. And this is actually at the core of a lot of the research that I've been doing. Um, but you see it even in like, yeah, the idea of game theory, right? How do we understand decision making in human contexts? Well, we do it by thinking about life in the frame of games. And so this is just an introductory session where basically I am playing the game of ironing out all the bugs. I don't know how any of this is going. I'm trying Restream for the first time, right? Um, and mostly I just wanted to, yeah, have some fun with it. And so, how many people use software every day? If I had people in attendance, and I don't actually know if I do or not because I can't see that. Um, okay, doesn't look like I have any comments or anything, which doesn't surprise me at all because nobody really knows I'm doing this yet, and that's totally fine. But most people use software all the time, and they just never think about it. Does anyone actually understand why it works when it does? Do you understand what it's supposed to look like when it works? I would guess many of you don't. My problem is I know exactly how it's supposed to work, and I know exactly what can't possibly work. And that's been a great deal of pain for me because I see what should be the case and then what is the case. Um, and those are very, very different things. So let me pose this question. What if programming isn't about code at all? How does that feel? Okay. So let's step away from programming for a minute and go into games. So let's assume that a game is a set of rules about what's allowed to change and what players are able to observe after that change. Now, let's go ahead and flip over to Cursor here. Not familiar, Cursor is an IDE, um, integrated development environment. It's based on Visual Studio Code, and it is one of the top AI powered IDEs right now. I tend to use Cursor because I like being able to see the code. The other popular one right now is Claude Code, terminal based. You might hear a lot about that. And we'll do some stuff actually with Ralph later. Um, Ralph Wiggum. Just gonna leave that there. That's just a weird tease that won't make any sense, probably, unless you've spent a lot of time on Twitter. It's been kind of popping off there the past few days. But I like Cursor in this case, especially because I want to demonstrate something. Um, so let's work on So I'm just putting a couple things in here into cursor. Um, and so I'm asking for a basic game engine. This is the core mechanics of a game. And so, you might hear like the Unreal Engine if you're into video games. So the Unreal Engine is basically what controls the physics of video games, and so when we think about the set of rules that are determining what changes are allowed in the universe, that's physics, right? Physics determine how a ball throw ends up. How much force did you use to throw the ball? What is the angle of the ball, right? We have all these rules that we can learn about how to understand the world around us. And so a game engine is just all of these rules combined into one, right? So we're going to design a basic game engine, just super, super simple. And then I have my definition of rules about what's allowed to change and what players are allowed to observe after that change. Let's see what happens. If I have the right window select. Okay, now it's going to go ahead and do some stuff for us here. If you notice, I also indicated Python as the language of choice. Um, I like it because it's simple, readable, which again, less important now, but basically, I just like to have a. I'm just picking it as a default for my own um, benefit, but that actually isn't necessarily. Now, if you didn't put Python there, what would happen? Well, it might write Python. I write TypeScript. Might write C++. I don't know. I didn't want to leave that up to chance. And so when I'm building anything, I try to be as specific as possible about what I want, because that's the rules that the AI is going to kind of use to build stuff. And this is the problem with LLMs. The rules are not set in stone in terms of what LLMs can actually do. So sometimes they think they can do things, they can't. Sometimes they don't know that they can do things that they can. And sometimes, you get lucky and you have an AI system that actually knows what it can do and then uh, chooses to do that when appropriate. That is the ideal AI system. Now, one of the things that we'll see here is that it's actually very, very hard, uh, the way things are currently structured, to uh, make a definite, like, probability. Like, so you need to understand one thing about code, and this is one of the things that I learned the hard way uh, while building software for people who weren't, software engineers. There is a giant, giant gulf between this never happens and this almost never happens. This never happens is a completely unreachable state. This almost never happens means it's going to happen eventually and you need to be able to deal with it. That second one is a much, much, much more complex case, because even if it's a small probability of happening, it can still happen. And so if we go back to the idea of a game, and a game being what changes are allowed, this is the difference between allowed versus not allowed. It's a binary. It's not about how often it happens, it's about whether it can happen. Okay. Um, so what do we have here? Cool. So we have a game engine architecture. All right. So we have a game state. Now, state is an important concept in programming because it means what is the system currently. And so this is what the world looks like, right? At a given time. And so if we start off, okay, well, let's go ahead and just run it and see what happens. So it tells us that it gives us a couple example games here. So let's do Python examples.py. Okay, so there's a counter game. Player one, increment, allowed, action applied successfully. So here's the state now, counter one. So this is a simple game as to like, are they allowed to increment the counter? So player one increments, counters at one. Player two sees counter at one, increment two, increment three, increment four, increment five, and then we hit six. Now that's denied. Okay, so why was it denied? Well, I don't know. Let's go ahead and ask. This is the thing that I really like about using cursor here. You have the ability to ask questions. So if we look here, how the counter game works, it enforces a maximum value via a transition rule. Okay, so if we look, this is showing us the code from examples.py, which that's what we ran here. And it's initialized with a max value. So initialize, that's the state of the game, or, we create an instance of the game. So an instance is a specific like copy of the game, right? So this is like one of the times we're playing the game. And so we create this game and we say, hey, here's a rule. And it has the rule is that there's a max value of 5. And so it stops it. Rules about what changes are allowed. Obviously, this is a very, very trivial example, but it's a powerful way to understand systems, right? Because it doesn't matter if you have a super powerful computer that can calculate any number of numbers being added to this value of 5. Doesn't matter how big the number is you want to add to 5. Doesn't matter if it's 1. You can't add anything that would increase it over 5. It's a hard, fast rule. Which means there is no state possible where the value of the counter is greater than the max value. Perfect. Okay, so now there's a different game. And this is hidden information, right? Okay, so this actually shows us how two players have different information available to them. Okay, so if they look, they both see the same turn, right? And then Alice has 5 public resources and 10 private resources. And then she can see Bob has 3 public resources available. Okay, so with Bob, it's still turn 1, but he's got 8 private resources available and 3 public available. And then he sees that Alice has 5 public resources. Okay, so transfer action allowed, action applied successfully. I don't know what that action was. It transferred something, right? So after the view, okay, turn stayed the same, but Alice has private resources down at 7. Public stays the same. Bob stays the same. So Bob's view shows that he has 11 private resources now, but still 3 public, and still sees that Alice has 5 publicly. And now, so this says, okay, so this transfer, if we look at, the state of the game that we can see here from turn 1 to turn 1, still apparently, we didn't update the turn, but we see that 3 resources moved from Alice's private stash and seemed to show up in Bob's private stash. So we assume that this was a transfer of 3 from private to private. And then we try a second transfer, and it was denied because insufficient resources, has 7, needs 100. So my guess is that we tried to transfer 100 from Alice's private to Bob's private. That was denied. Let's go ahead and ask it, ask Cursor to explain this. So again, we didn't look at the code. We only looked at the outputs that we can see, right? So we're looking at the world and how it changes between, changes after actions. So something changes. We can see different things, but, you know, we haven't looked at the actual code that tells us what things work, or tells us how things work. And so, okay, so here's the observation rule. Private resource observation controls what each player can see. You can see your own full resources, can only see others public. Okay, so this, again, that's what I described as I tried to figure it out. And okay, so it checks for available resources, deducts 3, adds 3. Right? Okay, and so that's what we thought. Now we tried to transfer 100 from Alice to Bob. That failed. Not enough resources. So we see information asymmetry, right? Players have different information available. You have private versus public. Some information is available to only you, some of it's available to everybody else. We have validation, and we have observation, right? So based on what you can see, limits the types of moves that you're likely to make. Okay. Now we look at a turn-based game. Player 1 scores invalid, player 2 scores out of turn denied because this was invalid. Player 1 ends turn. Okay. Current turn, player 2. So this is making sure that players are taking turns, right? Because, okay, so player 1 tries to do something on their turn, it fails, so the turn doesn't switch. And then player 2 tries to do something while it's still player's 1 turn. Well, you can't do that. So we have to hit the player 1 ends turn before player 2 is allowed to move. Okay, so this game enforces turn order. Only the current player can act, and turns advance sequentially, right? So there's rules. So it validates that it's the turn of the person who was trying to act. Then there's a turn advance rule. Do we transition to the next player? Okay, and so there's no handler for this score action. Okay, so it's invalid. That's fine, but it didn't change the turn state. So if we go back to the idea of state, right? The state is that it's player one's turn. Player two tries to do something. Nope, it's not their turn. Okay, now player one ends their turn. Cool. Player two scores. It shows up as invalid because there's no handler for it yet. But it's allowed based on the rules. Just there's nothing to do in that case. And so this gives us a pretty good overview of some different types of games and how those can work. Okay, so let's go back to the definition of a game. Rules, change, observation. What rules are enforced? What changes do those rules allow or not allow? And who is allowed to see the changes that occur and which changes occur? So this gives us the ideas of like the state, right? The state is what the game currently looks like. At any given point in time, the state of the game is how everything exists. A move is some sort of change in the state. And so you go from state one to state two. And then there's some sort of observable outcome. You already know what these things are. We're just trying to name them now. And so these are what we're going to use as the basis for building anything. Because you can build anything with just these three ideas: state, move, observable outcome. And now I'm going to introduce you to a really powerful idea. It's called a state machine. Now, if we okay, so I want to introduce you to the concept of a state machine. So let's add a game that teaches that to the player. Now, a state machine is exactly what it sounds like. At a state, everything can only exist in one state at a time. And then there are rules that transition to different possible states. And so a state machine has some number of possible states and select transitions that allow transitions only between the specified states. And so if you kind of think about this, if you have a state machine with only two states, state A, state B, and a rule that moves from A to B, you can go, if you have state A, you can go to state B. Now, if you're at state B, based on what I just said, you can't go back to state A. If we had another rule that says you're at state B and go to state A, then suddenly you can go from A to B, or you can go from B to A. Sometimes states will go to themselves, state B to state B. And so, okay, let's see what happens here. So this gives us a four-state machine. The states available are idle, running, paused, finished. So you can go from running to finished, or you can go from paused to finished. Now, if we go ahead and run the examples again, here is our state machine. Game example added on to the end. Teaches you about state machines. It has four states, just talked about. Current state, idle. From idle, it can only go to running. Cool. We started. Awesome. Now we're running. Remember, we can only be in one state at a time here. Okay, let's pause it. Cool. Now our current state is paused. All right. Now we can resume. We go from paused to running. We go from running to finish, complete it. Now we are finished. It's a terminal state because there are no more transitions possible. Can't go backward. Terminal state. Go pause? Nope. This means that a state machine has very, very specific rules about what can happen next and what states you can get to. Again, this is an incredibly powerful concept because it makes behavior predictable. Now let's think about a more complex game. Oh, we have a person in chat. Welcome. And okay, so now we've got the concept of a state machine. When we're dealing with really, really complex systems, it can be really hard to see all possible states. And when we have what are called non-deterministic systems, you end up not really being predictable. And so let's think about Twitter, for example, or X, if you prefer. Um, so we have a player on Twitter. What is the game that they are playing? Okay, so if we think about the game again, we've got rules around what changes are allowed. Um, we have the uh, man, sorry, got the rules, the observable changes, um, and then the actual like changes that you see, right? So you've got the okay. Anyway, so the state of Twitter is the timeline. Okay, so we observe what the current state is. It's whatever people are talking about in the timeline. What changes are available according to the rules? Well, you can interact with somebody else's post, right? You can reply, you can like, you can comment, or retweet, whatever. Then you can write your own post. One adds to the timeline, one modifies something on the timeline. Okay, so these are the set of rules that we can take away from this. Now, what is observable here? Now, this is where things get interesting because there are a lot of things that are observable to only you, and the game will have no idea about any of that. Like, what's your existing offline relationship with the person that you're interacting with? Twitter has no idea, but you do. What's the goal of the interaction? What was your intention behind that? Again, Twitter doesn't know. The person you're interacting with may or may not know. Depends on if they can figure it out from what you say. You know, do they have the same understanding of the relationship that you do? In my own experience on Twitter, mostly no. Twitter's really bad at helping people learn how to form real online relationships because it has all of these skewed dynamics and it's a very, very complicated system where there aren't clean state transitions. It's not a game that is easily winnable because you don't understand what all the rules are, because different people are playing by different rules. And we're really bad at understanding how to observe from different people's points of view. If you reply to somebody who has 100,000 followers, your reply is not going to show up very clearly to them if you don't have a lot of followers, probably because it's going to be buried. There's all these different like ranking mechanisms that determine who gets seen and by who else. And that's why a lot of these social platforms end up dying out over time because there's not a very specific game that is being played. And the larger a system gets, you have all of these little pieces that are independently predictable because you've got code that is running the rules of the system, but there are so many different connected systems and different connected games, you can't possibly observe all of the different states. And so, when we're looking at something like a clean state machine, you have only a set number of states and a set number of transitions. When you have a complex system, you don't have anything nearly as clean to build on. And so you've got to create a game that you can play and win. What does this have to do with building your own software? Well, the most important thing here is that you have to know what game you are playing. And so when I'm building software, I think about games. Now, let's go ahead and work on another game. So, how do we figure out a game that determines the quality of software? Okay. And so I said, let's start by thinking about what states of software we can observe and how changes to the state impact the quality score. Okay. So I'm introducing a couple things here. So I want to understand the state of a given piece of software. What does that look like, right? So we have to define what we can even look at. What is observable in terms of the state? Um, and then we've got a score. So the score is actually part of the state too. And so if we think about how to score software, I want software to be predictable. Why do I want software to be predictable? Because predictable is cheap. Let me say it again. Predictable is cheap. Let's think about this in terms of AI credits. If I ask for something from Cursor, let's say, and I'm confident in what I'm asking for, and it gives it to me after a simple request, like this, right? So we've got a deterministic answer here, like it told us what I wanted. If I could predict this, then I only need to run it the one time. If I can't predict it and I don't trust this, I might have to run the same thing 3 or 4 times because I want to see if it gives me the same answer every time. The more uncertain you are, the more you have to basically ask verifying questions. This takes longer. This takes more credits. It's more expensive. Now, think about this in terms of state transitions. State machines are super cheap and easy to run because they're deterministic. So, how do we look at software quality to determine whether software is good or bad? We look at how predictable it is. Cool. How do we determine predictable? Okay. Complexity. The more things that can go wrong, the more things are going to go wrong. Every branching path in software is double error states, right? Because then suddenly you have to handle multiple cases. So complexity, there are different ways to measure this, right? Cyclomatic complexity is something that was beaten into my head as an early career software engineer. Basically, this means like how many branches of code, how many loops, how many, all of this. Our principal engineers hated cyclomatic complexity. And if you increased the cyclomatic complexity of your code, you would hear about it in code reviews. Okay, test coverage. So software engineers write tests. If you have a piece of code tested and you say, okay, if I go down path A, it behaves like this, and here is a code that's basically code that verifies code, right? So we say, if A, then B, we have a test. We say A, and we expect B, right? We validate that works. We can measure that. Technical debt. This is the fun one. Technical debt happens because there are trade offs in software design. People who want you to build software want you to build software fast. Software engineers want software that works. Entrepreneurs want software that makes money. It's a lot of different things pulling at the software, a lot of different games being played. Technical debt happens when you make trade offs. And you say, hey, I'm going to go fast now because I'll fix it later. And then later never ends up happening because there's always more stuff to add. Technical debt builds up over time. Technical debt, more complexity, more unpredictability, lower quality. Documentation quality. Now, this is interesting, right? This is not code, but it determines how easy it is for other people to change that code. If you have documentation that tells you how the code works and gives you this extra context, you can gain information about why decisions were made when they were made when the code was written. Can't tell you how many times I've gone over a piece of code and what idiot wrote this piece of shit software? Like this is junk code. And I look at the commit history and god damn it, it was me 6 months ago. Common thing in coding. But all of those decisions made perfect sense at the time. Did we capture those? Okay. Code quality. Well, I mean, this is kind of what we're trying to measure completely, but you can actually like look for things like duplication. If you have the same code doing the same thing in two different spots, if you need to change that, you then have to change it in two spots. What are the chances you're going to remember that? Also, I mean, do they need to be the same thing both times? Like that's maybe, maybe not. And that's something that has to be determined by the person building it or the AI building it, depending case. Dependencies, right? These are how many things connect to this software that maybe you don't control directly. Um, okay, so we look at how many do we have? Do we have packages that are outdated? Do we have vulnerabilities? It's all stuff you have to pay attention to. Now we can measure all this, right? And then architecture. The architecture of a software system determines what that software system is capable of. If you architect the right system, building it is trivial. As someone who might just be vibe coding, you're not really a coder, you're an architect. But that sounds really hard because if you look at the hierarchy of software engineers, usually you're like, you don't get to an architect until you're a senior engineer with 10 years of experience, maybe, before you're hitting that architect level. But if we use the concept of games, you don't need to understand all of the difficult parts of software architecture because you're probably not building large scale distributed systems that need to hit all sorts of concurrency criteria and service level agreements, which are legal agreements that determine how software has to perform. If you're building something for yourself, you don't need to worry about any of that, but you do need to worry about the game you're playing. And again, that's why I'm focusing on this idea of games. It's a lot easier to be a game designer than it is to be a software architect. But in an AI powered world, those two things are the same thing. Okay, let's think about what we can look at here, maybe to finish up. I feel like I have dropped quite a bit in this first hour. I scheduled 2 hours because I wanted to make sure that I have time to cover things and just see what happens. But let's go ahead and talk about the rest of the course. And so I have it set up over the next 10 weeks. And let's see. Let's go close some of this up so we can actually see what we're doing here. Uh, okay. So module 0, right? I guess the one thing we didn't get to here is really the idea of like winning and losing. Really depends on who the observer is and what they see. We didn't actually use these games because we just had cursor built our own. But we talked about things like hidden information, observable state changes, simple state transitions, right? We talked about state machines. So here's your exercise. If you want to apply what you've learned, invent a game. Players can make moves, but only some of those moves are visible to others. Then you have to see what you can get to. And if you do any of this, please share it on Twitter, on YouTube, on LinkedIn, and tag me. I would be happy to share what you're doing. It's really hard to get things visible online right now. It's a very noisy environment. And so if you're putting in the work to learn programming via game design, I would be more than happy to help you share that because sharing your work on the stuff that I'm sharing helps me. And that's the game I'm playing a positive sum game where we can all win via cooperation. Okay, next week, we're going to talk about time. and changes. Time doesn't matter, changes do. Change and progress are not the same thing. Just because something changes doesn't mean it's better. If a change isn't observed, did it happen? Tree falls in the forest, doesn't make a sound. I don't know. What's observable versus what's latent? Can you see it or can you not? So we'll talk about some different games here. We'll probably actually create some of our own again using cursor. I don't know. That was kind of a fun way to do it. Um, and then we'll maybe design a game where you have two different ways to do it. You either announce the move or the outcome, not both. Um, and we'll see if time felt different. So, we can really do some cool things with time here because it's not about how long something takes, it's about what changes happen and who can see it. Depending on the system, two moves can be the same and take different amounts of time, but it's all about the changes. Okay. So then we'll go into module two, players as observers, rules as programs, state, memory, and score, right? Like we're getting into more of the details. Time is what players notice. Okay, that gets interesting too. Um, bugs. Bugs are changes you didn't expect. Then we'll get into multiplayer. Distributed systems, that gets interesting because then suddenly things are happening at the same time, but are observed at different times. Whew, that makes things crazy. And finally, we're going to go into designing for humans, and then we'll kind of like talk about code a little bit at the end. And then finally, we're going to design a playable system. So I want to see people actually present. If I have enough people start picking up, participation through the journey, we'll maybe even have a demo day. I don't know. We're gonna play it by ear. Like I don't know how this is gonna turn out, but I think this is a really important way for people to understand software and code and the concept of the internet, right? As a game to be played with their lives. You can use this as a way to observe details about your own life and create games that bring about the changes that you want to see in your life. This is where it all comes together. If you have games that determine the changes and you know what changes you want to experience, well, then you can connect those, right? That's where this becomes incredibly, incredibly powerful because the faster you can observe a possible change that you can implement, the faster you can make that a reality by creating a game that defines how that change occurs and what observations help you know that you're getting to the outcome that you desire. Suddenly, the world is your oyster. Reality becomes very, very, very malleable when you understand what reality is. And reality is a set of shit that's either changing or not. So, what changes are you currently observing? And which ones aren't you? All right. I'll see you next week, 11 a.m. Eastern on Thursday. And we're going to talk about change before time. 'Cause time doesn't matter, change does. And with that, I hope I've given you a little bit of change, or at least the possibility for change in your own life. Hope you learned something. Uh, if you watch this, give me some feedback. Let me know. Uh, I can only get better at what I'm doing if I have people actually telling me what that I'm not like things that I'm not good at, things that don't land. Right now, I'm talking to the void. I can't observe the changes that I'm creating in you. And so I need the other players in the game to start telling me what changes they observe in themselves when they go through this. And from there, we'll figure it out together. And with that, I bid you adieu.